Okay, so welcome to Rocks and Ice in the Solar System, presented by Mount Diablo Astronomical Society. So did everybody get their strip of paper? All right. And like I said, we're going to be talking about the rocks, the ice, where they are, what they have to do with meteors, meteor showers, and how it all goes together. So let's go. There's one thing that I want to start out with. I like to start out most of my public programs this way because this is a misunderstanding that a whole lot of people have. And that is the difference between the solar system, the galaxy, and the universe. Some of you may have experienced that. So let me start my screen share again with this share. Okay, so I'm going to close this down a little bit. There we go. And so the solar system. Now, how many stars are there in the solar system? You can hold up your number of fingers if you want.
Do you want us muted, Marnie?
It's up to you.
So there's one in our solar system.
Yes, one in our solar system, exactly. And I'll often get answers like millions. And that's why there's that confusion between the solar system, galaxy, universe. Our sun, bunch of planets, and a whole lot of leftovers from the formation of our solar system. That's our solar system. So let's move on to what the galaxy is. The galaxy is the sea of stars that we live in. We're one star among the hundreds of billions in our galaxy. And there we go. And we're roughly halfway out in our galaxy. So, and then the universe is all the galaxies. In other words, everything there is that we know of. Billions and billions of galaxies. So I'd like to make that clear with folks, and so everybody's on the same page. But today, we're going to talk mostly about the solar system. In fact, completely about stuff that's in the solar system. The thing that you can see from this NASA image is that they're actually showing the orbits roughly circular, which is roughly what they are. They're not perfect circles, of course. And but they don't show the relative sizes between the planets, nor do they show the relative distances, the actual distances, to the sizes here. So that's often a confusion because people don't understand how far away things are in our solar system. There is a reason they call it space. So let's do an exercise. Get out your piece of paper. And is that where yeah. So, well, first of all, I want to go over this little bit here first. There's 4 rocky planets, inner rocky planets. There's 4 gas ice giants. There's a rocky asteroid belt. And there's a rocky, icy Kuiper belt out here. Now, the belts aren't exactly in a nice, neat thing like that. They're actually all over the place within those realms. And so what we're going to do, we're not going to build a model of the sizes of the planets relative to each other and to the sun, but we are going to do one that is relative distances. So I'm going to move over to, and I have behind me, if you're curious about what I have behind me, this is a banner that has the the orbits of the 4 inner planets, the asteroid belt, Jupiter, Saturn, and a bunch of stars around. I don't know if you can read them or not, but they're the stars of the ecliptic. They're the constellations that are in the same plane as our solar system. That's what zodiac is all about and all that. But that's not for this session. That's for a later session. But these stars here are a minimum of 20 miles away on this scale. And the size of the sun on this scale is about the size of this little dot. You see that little dot right there at the end of my finger? It's like you take a pencil and just make a little dot right at the end, right at that point. So that's how you're going to start your pocket solar system, the scale model. But it's to that scale where the sun is that small. So you know that the planets are way too small to even see. So I'm going to turn it over to my buddy Vivian, and she's going to take you through the pocket solar system.
People often think the orbits of the planets are more or less evenly spaced and closer together than in reality. Building scale models of the solar system is a challenge because of the distances and huge size differences involved. This is a simple little model to give you an easy way to demonstrate to any number of people an overview of the approximate distances between the orbits of the planets and other regions of our solar system. First, everyone watching this must participate. Have each person pull off a strip of register tape about the length of the person's body. That's about fingertip to fingertip. Cut or fold over the ends so that they're straight. You'll want to label one end Pluto/Kuiper belt and the other end Sun. This will be our baseline, the average distance between the Sun and Pluto's orbit.
Okay. Go ahead and get that part done. Okay. Next, here we go.
Fold the tape in half. Crease it and open it up again. Make a mark at that crease. Let's think about the planets of the solar system. Which planet do you suppose is halfway between the Sun and the average distance of Pluto's orbit?
Okay, any guesses? You can unmute yourself or just hold your space bar down.
Jupiter?
Jupiter's a guess.
Saturn?
Saturn's a good guess. They're all good guesses. Okay, shall we find out?
Let me give you a hint. You need to be careful about using this hint. It depends a bit on your audience. If you hold the Sun at your head and Pluto at your feet, which body part is halfway in the middle? Right. Very good. Bet you'll never forget which planet it is.
Okay. That's a great one to do with kids. They really love it. So it's Uranus. It's not even showing on here. It's way out than what I have on here. Okay, let's continue.
Now fold the tape back in half. and then fold it in half again. Make a crease there. Now unfold it. You have the solar system divided into quarters, with the sun at one end, Pluto's orbit on the other, and Uranus's orbit in the middle. Hold the Pluto end and label the fold closest to Pluto as Neptune. Label the other fold closest to the sun as OK. Everyone guess.
Okay, you got an idea? All right, let's find out.
Right, Saturn. Here's an easy way to remember the order of these three outer planets. We know there's a sun at the center of the solar system, but there's also a sun, an S-U-N, in the outer planets. Saturn, Uranus, and Neptune. S-U-N. Okay. You've mapped out 3/4 of the solar system, and you still don't have all the gas giants. So we have to fit everything else in that last quarter between the sun and Saturn. Let's keep going to see how this will work. Fold the sun to Saturn's orbit. And crease it. What's the next planet in? Right, Jupiter. Fold the sun out to meet Jupiter's orbit. Now this is a little tricky. Which structure did we say is just inside Jupiter's orbit? The asteroid belt. At this point, things start getting a little crowded and folding is tough to get precise distances. Fold the sun to the asteroid belt and crease it. Next planet in? Right, Mars.
Okay, is everybody caught up? Everybody ready? Okay.
Label that. How many more planet orbits do we need to place? Yes, 3 more orbits. Now fold the sun, the orbit of Mars, and leave it folded. Fold that section again. Fold that section in half again. Unfold the tape, and you should have 3 creases. Mark Earth on the crease nearest Mars, then Venus, then Mercury closest to the sun. Earth, Venus, Mercury. Have your visitors stretch out the model and take a good look at what they've made. Many people are unaware of how empty the outer solar system really is.
Okay. So, what do you notice? What do you notice about this?
A lot of empty space.
A lot of empty space, yes. Anything surprise you?
How close we are relative to the full space, how close
Yeah.
to the sun.
How close to the sun we are. We have to be this close in order to have a habitable world here. So I'm going to put this on, I've got a piece of tape here. So I'm going to put this piece of tape on here and line up that little dot of sun right over the sun on this banner. Then I'm going to stretch this out and perhaps you can get, oh, I see you can't see me anymore, can you? Here we go. I'm going to stretch this out so that you can see why we can't have a giant banner, right? Why we can't make a banner that's 12, we would have to have a banner that was 12 feet across, 12 feet each way. And so that's why this stops with Saturn. But if you make a pocket solar system, you can actually illustrate where the other planets are. And so, and you can see how close in the asteroid belt is versus the, do this, I turn around and point it that way, versus the Kuiper belt way out there. I'll make it so that you can kind of see what's behind me here, especially if I stand over here a little bit, look in like that. So you'll notice that this more or less lines up with the inner planets, asteroid belt, Jupiter, Saturn, and so on. It's a rough thing, but at least it gives you the general understanding of how far apart they are. So there's rocky stuff in here. Why do we have rocky stuff in here without hardly any water or ice? We've got water and ice on our planet. There's ice on Mars, and Venus is too hot to have liquid, to have anything but vapor. And then and Mercury, no. So as we go out, we have to get out to the outer solar system before it's far enough away from the sun that you get vast quantities of ice. And so the asteroid belt is a bunch of rocks. Very little, if any, water ice in there, or ice of any sort. Way out in the Kuiper belt, that's where the rocky, icy bodies come from, the comets. The comets come from that rocky, icy area out there and from the Oort cloud. The orbits of the comets are generally decades to many years, and the ones from even farther out on this scale, they'd be about the Oort cloud would extend about two miles out there, but I'm not going to talk about the Oort cloud too much today. But has everybody seen a comet? Raise your hand if you've seen a comet. Everybody knows, right? Okay, good. So especially the last one that just came through, which was a thrill. So that's where meteor showers come from, is the comets that coming into the inner solar system. And they don't actually start showing their tails until they get in to right about in here between Saturn and Jupiter, because they have to get warmed up in order for the ices to start turning into gases and releasing some of those rocks that the dirty snowballs, perhaps you've heard that as the term for a comet. Now, well, yeah. And so as their ice turns to gas, it releases some of the little bits of dust that are on within the comet. Yeah. The other point is that now the main asteroid belt is also full of little bits of dust, as well as asteroids. Asteroids are generally many feet to many miles across, but the really big ones are less likely. It goes down so that you have a whole lot of little ones, but not very many big ones. And it's the same is true out there in the Kuiper belt. And remember, the Kuiper belt goes all the way around like this, all the way around us, about 6 feet in each direction here, plus farther. Right, and that's the rocky, icy stuff.
Marnie?
Yes?
Do all are some comets way further out than what's considered the Kuiper Belt, or does that include all
Yes.
comets?
Yes, some comets do come from much farther out, like Hale-Bopp. They figure Hale-Bopp came from the Oort cloud, which is this, I should probably start with when the solar system was born. When our star was born, it came from a cloud of gas and dust 4.5 billion years ago. And most of the mass went into the star, but there was a whole lot of mass left over, and a lot of it went into the planets, all the leftovers, but then there's still a whole lot of leftovers after that, the rocks and the ice left over. And it goes out way far and like I was saying, the Oort cloud, we don't have any, we have statistical evidence for the Oort cloud because I forgot how long Hale-Bopp's orbit is, but it was like 1,000 years or something before it comes back again. Whereas the ones from the Kuiper Belt, closer in, and yes, it goes way out there, all the way out, but there's a belt out there that most of the comets come from, and those are decades. Those are in the decades. So, but comets and asteroids are feet to miles across, mostly miles. But the particles that come off them are very tiny. They're like sand, pebbles. That's how big they are. And so if we had a golf ball size meteor coming through the atmosphere, if you had the fortune of seeing a golf ball size coming through the atmosphere, that would make a big streak through the sky. So whereas the little ones still make a streak, but they're not that big. The parent bodies are huge, but the stuff that gets sloughed off them is not so big. That debris that comes off them is not so big. Actually, why don't I show you an illustration of what this looks like? Most meteor showers come from comets, and so let's see an example of this. This is something called meteorshowers.org, and now this is called meteorshowers.org. This is Comet Swift-Tuttle's that makes the Perseid meteor shower. Here, let me brighten up my cursor again. This is the path of Comet Swift-Tuttle as it comes into the inner solar system and then goes out again. If we come back out, you can see that it goes way out here. This line out here is Neptune. This is Uranus, Saturn. I'll go back in, but you can see that. So you can see that it originates out in the Kuiper Belt. And then you can see which direction it's flowing, because this is all the debris that it leaves behind as it comes into the inner solar system and then back out again from the tail that comes out of it. And all that debris is still in orbit around the sun. So this is from the Perseids here. And you might take a look at the dates here. That's July. Let me quickly move in to the inner solar system. The blue is Earth. Let me slow this down. Okay, I'm going to slow this down a little so that we can See, here comes the Earth. Now, when are the Perseids? In August. Look at this. There it is. See, it went right through. This is the point where the comet crossed the orbit of Earth and left behind all this debris. Now, here we come again. There it is, running through the trail that Comet Swift-Tuttle left behind. That's the Perseids in August. August 12th is usually the big one. There it goes again. So here's the Sun, Mercury, Venus, Earth, Mars, and then we go out and we can see the rest of it. But you can see that the comets are not coming in the line, in the same plane as the solar system. They're, they have very elongated or elliptical orbits. But we've got the Geminids coming up in January, so let's take a quick look at that. Whoa, what's that, right? The Geminids is a meteor shower, but its parent is from the asteroid belt. It's a asteroid called Phaeton, and on your handout, I hope everybody got a copy of their handout too. There's some links that talk about this particular meteor shower being from a comet, from an asteroid instead of from a comet. But you can see even that is at an angle. Its orbit is at an angle to the plane of the solar system. But here we come. Let's take a look and see if we can figure out where it's crossing the orbit of Earth. Looks like it's right here, right? So let's watch Earth come around. Can you see the little blue dot that's Earth? It comes around. Watch the date over here. And it's coming around, and we're approaching December, and here we go. Bang, there it goes, and out the other side. So this is an illustration of, see, now the asteroid comes in, oops, the asteroid, comes in this way and then goes back out that direction. Now, the material that's moving through here, is coming into our atmosphere at roughly 10 to 30 miles per second. So that's pretty fast. And so what makes that streak through the sky? So does that help explain? Do you like that animation, or have you seen it before?
No.
Haven't seen it?
No, it's great.
Yeah, I just discovered it a couple months ago. I was so pleased to find it because I like it because I think that it gives a good illustration of what these things do.
And that worked really well with the pocket solar system.
Yes. Yeah, it does. That's great. Oh, by the way, I probably should show you what do meteor showers look like, right? Or meteors themselves. Now, this is an image that was taken at the Geminid meteor shower 2 years ago, but you can see they're little bright streaks through the sky. But is this what you think you're going to see when you look up? Are you going to see all these things coming down at once?
No.
No. It was taken over about 4 hours, and then they were all stacked together so that he got several streaks of the of the meteors that are coming through. And you may notice that here is Castor and Pollux of Gemini. And so the meteor shower is generally named after whatever constellation in the sky they appear to be coming from. And I can talk about why they appear to come from a particular constellation, but it has to do with the Earth's movement through space and its direction of orbit and so on. Okay, so really what a meteor looks like is this, one streak. So what's going on there? Why do we see a streak? If we've got little tiny things like little bits of gravel and sand and that kind of thing, why does it make such a big bright streak? That's because it's been flying out there. I mean, these particles are billions of years old. They're the leftovers from the beginning of our solar system. And so they have been flying around out there all this time, minding their own business. Now suddenly they're attached to a comet, or in this case, an asteroid that has come through, gotten warmed up, and is throwing off some of that debris. And one of them happens to come right through our atmosphere at these incredible speeds of 20 miles per second or so. And when they come through, they actually heat up the atmosphere. They ionize it, if you will, and cause the atmosphere to glow. And in the process, the little bit of dust or whatever disintegrates, but it leaves this trail of heated air, if you will, and it's the ionized gas that you're seeing, the ionized atoms that you're seeing as the little bit of stuff comes into our atmosphere. Now, a lot of people don't know how high up meteors are. So let's take a look at another picture that might give us a hint. This picture was taken from the International Space Station in January of this year. This is Edmonton, Canada, right here. And Christina Koch saw a bunch of little meteors down below her. Now, the space station is up roughly, 250 miles or so? And so what does that tell you about where meteors are? Below the level of the space station or higher?
Below.
Below, of course. So, and actually it's about 50 miles up in our atmosphere, where the atmosphere is thick enough, is dense enough, so that the meteor, the little bit of stuff coming into our atmosphere actually can do some damage and create that streak. So about 50 miles up.
So it's the ionization of the atmosphere,
Yeah.
not the particles disintegrating and becoming incandescent.
No, it's not.
The light.
That's a common understanding, and it's not the way it happens. The effort of coming through the atmosphere causes the thing to disintegrate, but it doesn't burn up, so to speak. It actually heats up the atmosphere coming through, creating that little streak. And that's why they're so short-lived. If you have a golf ball size coming through, you've probably seen a few fireballs, and let me stop the sharing for a while. A fireball come through and that trail stays there for a long time because it really heated up the atmosphere, and so it stays glowing for several seconds instead of just a couple.
How large must a meteor be to become a meteorite and actually strike the Earth?
Yeah, a meteorite is a rock that was out in space called a meteoroid that comes into our atmosphere, creates that streak, which is called a meteor. And then when it hits the ground, it's called a meteorite. You know, it's the same thing, you know, but that's the way sciences are. So when it has to be about this, my understanding, what I've been told by the scientists is it has to be about the size of a VW bug, you know, an SUV kind of size even, to leave anything at all in the size of a meteorite. It doesn't disintegrate completely as it comes into the atmosphere. However, all these things that are disintegrating in our atmosphere, it's all raining down onto the planet. And there's roughly 2 semi-loads of space dust that hit the Earth every day. So, you know, about several tons.
So, Marnie,
Yeah.
if I understand correctly, one of these that actually reaches the ground, it roughly needs to be approximately the size of an SUV. Things that are significantly smaller than that are not going to reach the ground.
Right. They will disintegrate completely as it comes through the atmosphere. And the other thing is that when if an SUV SUV asteroid came through, meteoroid, excuse me, came through our atmosphere, it would probably break up too. And it leaves a trail of meteorites on the ground. Yeah, pretty cool, huh? Why early morning, right? It's always said that meteor showers are best after midnight. We always tell people meteor showers are best after midnight. But here's a nice little way to explain why. I call this kitchen astronomy. And I've got a lot of little things like that are kitchen astronomy. Let me do this again. Spotlight. There we go. Okay, so why are meteors best after midnight? You yourself can demonstrate this in your own kitchen. All you need is some pepper or some other spice that, you know, have little particles. And I mean, pepper's about the size of some of the bigger particles that are left behind. I would say that something like chili chili powder is even finer, and that's more like the stuff that comes off of comets. So you need some pepper to represent the debris left behind from the comet coming through the solar system. You need a cap to represent, oh, here I can do this, right? And the pepper represents the debris. This light represents the sun. And then you need a little cap of some sort with flat bottom that's round, like the Earth. This is like a slice through Earth, little slice through Earth, so that it's got a circular side so that it kind of looks like a little piece of a globe. And then you need a flat, smooth surface. You can't do this on a carpet. No. So you have to do it on a smooth, flat surface, like a countertop in the kitchen. Okay, so here we go. What you do first is you prepare the surface to become the trail of debris that the Earth is going to be passing through. And I just sprinkle the pepper on there. You turn on the sun over here. You can see the direction of the sun from the shadows of the particles and from the shadow of the Earth. You can see this is the day side. This is sunshine side. This side is the night side over here. And now this spot, oh yeah, that's right. And this is the direction of Earth's orbit that Earth is traveling in its orbit around the sun. Okay, now this line right here, is that sunset or sunrise, would you say?
Sunrise.
Sunrise.
Very good. Yes, that's sunrise on that side because the Earth turns this way as it orbits, as it rotates. So there's sunrise, morning, morning. All right, now we're going to look at the other side where sunset is. And in the middle, we're going to call midnight. So why are meteors best after midnight? Here we go. And there's the direction of Earth's rotation. Remember, here's the sun again down here. So then we take our Earth, and I just use a stick or something. You can just use your finger to push it through if you want. And you start pushing it through the trail of debris. Keep pushing, and let's see what the result was. Okay, what happened?
They're getting piled up in the forward direction.
They're getting piled up in the forward direction. So let's take a look at sunset, between sunset and midnight. Now look at this. This is pretty clean, right? You don't get that many meteors here. Now, this is a bit of a bad illustration because all of this stuff is still moving and orbiting on its own path around the sun. So you're going to get a few incidentals that hit the atmosphere. But if we look at the other side, midnight to sunrise, look at all this stuff that came flying into our atmosphere. Yeah. So you can see why midnight to sunrise is actually better. And you'll also notice that you don't have to get up at midnight to see it, because look at all this stuff that accumulates just before sunrise. So my favorite time to go out is like 4 o'clock in the morning and stay until like a half hour before sunrise when you can't see them anymore.
Money?
Yes?
When I've done sort of sidewalk astronomer type stuff with the public,
Yeah.
I've used, similar to your analogy, I think it's similar to yours, but what I use is a car driving on a lonely road after dark, after dark. And you get a bunch of bugs that smash against your front windshield, but you get very few bugs that smash against your rear windshield.
Right.
Front windshield is facing our direction of travel, and the rear windshield is not facing the Earth's direction of travel.
Yep. Do what you want to do. Do whatever works for the audience that you're talking to. And share it with your families, because that might be fun. So does that explain why meteors are generally best after midnight? Do you like that demonstration? Yes? No?
Yeah, it was good and effective.
Okay, great. All right. So last topic is, so where do we go to see meteor showers, right? I know that the current weather forecast just before this said that Monday morning, it still might be kind of cloudy. Yesterday, it said it would be intermittent clouds. So, pick the forecast that you like and go with it. But remember that the meteor showers aren't just Sunday night to Monday morning. They go for several days on either side. So if it gets clearer, which it's supposed to, on Tuesday, try going Tuesday morning and see what it looks like. But where do we go? Generally you got to get away from the city. But the nice thing about the Geminids meteor shower is that it's a heavy shower. there's like, what is it, 150 per hour, something like that on average, which is a huge fall, or yeah, a whole lot of meteors. I tend to drive up into the hills behind Lafayette into where Briones Park is. Just stop on one of the roads there because they're very quiet, they're very dark, and enjoy it from a place like that, you know, where you've got a nice open sky above you. So really any of the regional parks are pretty good places to go. Contra Loma, is that the one that's in East County? That one's pretty good too. So anybody else have any suggestions? But of course you can just do it from your own backyard too. Or
I mentioned on an earlier post, Lake Del Valle and Livermore. It's a little, you know, takes me about an hour to get there, but that's good. And also Big Break
yes,
over at the Delta in Oakley, which is really close.
Yeah, which is, it's farther away from some of the towns. Absolutely. So yeah, it's just that the lighter it is, the fewer of the meteors you're going to see, but you're still going to see a reasonable number, even just don't be in the brightest part of the city of wherever you live. And so fortunately we have a lot of open space around here.
I live fairly close to, I live within walking distance of the Alhambra Creek entrance to Briones Park off of Release Valley Road.
Perfect.
And I watched the comet, the Neowise comet recently there. First comet I ever saw in my whole life. And I'm 74 years old. It was very, very exciting. And that right at where the gate is, where you would actually during the daytime drive your car in. You can't drive your car in at night, but you could walk in. There's a really nice a paved road for cars with no cars on it at night. Right. And there ain't no people there either, you know, and it's really, for these parts, it's pretty dark, and you see the entire sky. You almost see it from horizon to horizon. It's a great place to go. Excellent
suggestion. Okay, well, thank you very much. I hope you do have a chance to watch the meteor showers, and have a great day.
Thank you.
Thank you.
Bye.
Thanks, Marnie.
Yep, you bet.
Thank you, Marnie.